Today we'll discuss about modeling of DC motor, which is specifically field control. So yesterday I talked about the modeling of motor when you are going to control control the motor through the armature side. So yesterday we talked about this side as input. So we were feeding input voltage at the armature side and trying to control the output theta. Today we'll keep this side constant. So yesterday we kept this constant and control this variable. Today we'll keep this constant and try to control the input at the field side and study and or analyze the output theta, or we'll try to find the relation between theta and Vf, the field voltage, and we'll finally obtain the transfer function in terms of Vf and theta. Yesterday we found the transfer function in terms of V and theta. So just for the sake of quick recap, yesterday what we studied. So I showed you this image, and in this particular image if you see that DC motor has only two terminals. So this shows that the motor shown over here is a permanent magnet type motor. So for a separately excited motor, this should have a four terminals. So two for armature and two for field. So in case of armature controlled DC motor, what we do is we obtain the feedback and send the voltage signal to the armature terminals while keeping the field constant. While today, if we want to control the motor output using variable field, we'll keep armature constant, and the two set of terminals, the second set of terminals, the field terminals, will be fed with the feedback signal or the error signal. So this motor, if it had been a field controlled separately excited motor, should have four terminals. Now for an armature controlled DC motor, what we did was we perform analysis on the armature side with KVL being applied on the armature side, since field side was constant. So we didn't applied any sort of analysis on the field side, considering that flux was constant. So we took flux as constant, and that is why no analysis was done on the field side, while the VI, the armature side voltage, was variable, and hence we applied KVL, trying to study the dynamics at the electrical circuit of armature side, and then we studied the dynamics of the mechanical system, and we had a relation between the electrical and mechanical system given by this expression EB. So EB was EB was an expression that connected the electrical system with the mechanical system, expressions of electrical and mechanical systems. So we performed the analysis, we applied KVL, then we applied Laplace transform, and we then obtained the free body diagram of the load, then again applied Laplace transform, and finally obtained the relation transfer function. So this transfer function was possible, the mechanical output and electrical input. The relation was possible because of the intermediate relation that connects the electrical quantity with the mechanical part, which is nothing but the back EMF. So because of this relation, we obtained the connection between the electrical circuit and the mechanical system by this expression, and we further obtained the block diagram representation of armature controlled DC motor. And I told you that this is a sort of a negative feedback system, and how it puts the influence on the armature current when the load is increased or decreased. So now we talk about the modeling when the field side is being controlled. So we have certain elements here, like RF is the field winding resistance, LF is the field winding inductance, then we have VF as input field voltage, IF as the field current, and all other variables had been discussed yesterday. And thus the torque that is developed by this motor, given by Tm, is, so the expression that we studied yesterday was Kf, Ka, If, Ia. If is the field current, Ia is the armature current. So in this particular case, since we are going to keep VA constant, the armature side voltage is constant, and thus Ia will be constant. So we are going to assume Ia is constant, Kf, Ka and Ia are constants. And thus this can be written by an expression Tm Kt dash If. Now we see that the torque depends upon field current in this particular expression. Yesterday what we obtained was Tm was equal to KTIA, but now the expression is KT-IF. Now if we apply KVL on the field side, since we are going to vary the voltage at field side, and thus if you look at the field side electrical circuit, you have Vf as input, and the voltage supplied at the field side will be equal to IF RF plus IF LF LF DIF by dt. So voltage input is equal to the voltage drop taking place at the resistance as well as inductance. So this is the voltage drop that takes place at the resistance, and this is the voltage that cuts across the inductance. So if we take the Laplace transform of this expression, we get this all in terms of all becomes the function of S. And again, if you look at the motor torque experienced by this load, so for this we'll be drawing the FBD of the load. So suppose that J is the moment of inertia of this load, and the motor torque, the torque that is being applied by the motor, developed by the motor, is Tm. So this is the torque that is being developed by the motor, and the torque which is resisting the load are because of the viscous damping that occurs. It may be because of friction due to air, or it may be because of some other sort of frictions, air drag, or it may be working inside a fluid. So any sort of friction will be taken into account by the expression D. So we have viscous damping or the damping torque, which is equal to d by dt of theta. The second torque that resists the motion is because of moment of inertia J alpha, or d squared theta by dt square. So if we try to equate all the acting torque and the resisting torque, we get the expression Tm equal to J alpha plus d omega. So this is the motor, this is the torque that the load experiences. And if we see the equation 1, equation was nothing but the relation of torque that is developed by the motor was KT-IF, and we equate this with this expression to get this expression. If we take the Laplace transform of this expression, we finally get KT-IF function of S equal to S square J theta plus S d theta. So now we obtain the relation. This is a relation that we have. We want to obtain the transfer function where Vf is input and theta is the output. So if you look at this expression, you have theta, which is the output, while If is not the input. This is a variable that should be having a relation with Vf, and we'll try to eliminate this. So in order to eliminate If, we have a relation of If with Vf in equation 2. So from equation 2, we'll be obtaining Vf, and then we'll be substituting this in place of If in order to obtain the relation between input and output. So from 2 and this equation, hold a second. So from equation 2, we'll be trying to eliminate If in this particular equation. We'll put this the value of If from equation 2 in this relation to obtain the relation between Vf and theta is. Yes. So from the previous equation, from this equation, we further evaluate and simplify this to obtain theta s If in terms of theta s, and then we are going to substitute this value in equation 2 in order to obtain the relation between Vf and theta s. So this is the input while this is the output, and now we don't have any other variable apart from input and output in this particular expression. So from this expression, we get the transfer function as the ratio of output by input, which is nothing but kt dash upon rf plus slf into s square j plus sp. So this is the required transfer function of a field controlled DC motor. And if we try to obtain the block diagram, so as I told you that in case of block diagram, we are going to represent the input at the leftmost side and output at the rightmost. So input in this case is Vf while output is theta. So if you look at equation 2, which is nothing but the Laplace transform KVL equation of field side. So there you saw that Vf is equal to Rf plus SLF multiplied by If. So from this particular expression, you get the block. If you feed this input Vf to a block 1 upon Rf plus SLF, you get output If. So this is clear from equation 2. This can be written in terms of If as Vf upon Rf plus SLF, and thus this block. From equation 3, you see that If, and there exists a relation between If and theta s. So if you feed this particular variable into a block kt dash by s square j plus sd, which is obtained from this expression. So if this block kt dash upon s square j plus sd is being multiplied by if, this will give you an output theta. So this is what we obtain in this particular block. So now we see that this is the input and this is the final output. And we don't have any other signal going to the comparator. We don't have any comparator in this particular block. So we are going to straightforward connect these two blocks to obtain the final block diagram representation of field controlled DC motor. So this is the block diagram representation of field controlled DC motor. So I guess this is clear to all. And if you have any question, you can ask me or post me the questions. And if you don't, then I'll move forward. Okay. So assuming that this is clear to all, I move forward and now I talk about AC servo motors. So this was till now I talked about DC servo motors, and as the name suggests that AC servo motors will be operating on AC signals, and this is also a quite simpler topic because AC servo motors are not more than induction, two-phase induction motors that you have already been taught in your previous year. So there's a slight change in the constructional features compared to two-phase induction motor. So they are nothing but two-phase induction motors with slight changes in construction features. So two-phase induction motor with AC servo motors are two-phase induction motor with high rotor resistance. So one constructional change with respect to two-phase induction motor is that you're going to provide high rotor resistances. So you will be increasing resistance in rotors. And the reason that we do this will be explained in the upcoming slide. The two stator coils are separated by 90-degree electrical. So if you have these two coils represent the stator. The control winding and reference winding are provided at the stator of the servo motors. So as you did the same thing in two-phase induction motor, what you're going to do is you're going to separate them 90-degree electrical in space. So we call this as space quadrature. So I assume that you know about electrical and mechanical angles and the relation that exists between them. Even if in case if you don't, so I'll try to explain this apart from the scheduled lectures. So or I'll provide you any link to understand the relation between electrical and mechanical degrees. So we assume that they are separated by 90-degree electrical, and we call this as space quadrature. The reference winding, this particular voltage is a fixed AC voltage. And mind that we are always going to provide, since we are talking about AC servo motors. In case of DC servo motors, because DC motors operate with DC supply. So you'll be having DC voltages provided as input in case of DC servo motors. While in case of AC servo motors, you will always be providing AC supply to both the coils. So reference winding will be provided with fixed AC voltage. So this will be alternating in nature, but will be having fixed amplitude. While the control winding has a variable AC voltage, and that depends upon how you're going to control the rotor. So for the purpose of controlling the rotor, the voltage at the control winding will be changed. So the amplitude of this voltage will be changed according to the requirement of control of the load. And these two voltages, the voltage that is fed at the reference winding and at the control side, will be 90-degree out of phase to create rotating magnetic field. and this is the principal requirement for rotating your load that you should always have. In case of two-phase motors or a single-phase induction motor, you always try to generate two fluxes which are more than 0 degree out of phase. So if you have larger phase difference between the two fluxes, by flux I mean the flux that is being produced by this coil at reference winding and the flux that is being produced by control winding. So these two flux should have a phase difference more than 0 degree in order to achieve a rotating field, the experience of rotating field around the rotor. It's better that these two fluxes should be 90 degree apart to have the best rotating field at the rotor periphery. So we try to keep the voltage because of these. So these fluxes, because of reference winding and because of control winding, will be 90 degree out of phase only when you're going to keep the voltage, the reference winding voltage and control winding voltage 90 degree out of phase. So this is why we keep the two voltages 90 degree out of phase to create rotating magnetic field, and this is called as time quadrature. So this is different from space quadrature. So one requirement to in case of induction motor is that you should have both the windings 90 degree out of 90 degree electrical out of phase. So they should be situated 90 degree electrical. And the second is that the voltages that are being supplied to both the windings should be 90 degree out of phase. And the second requirement for AC servo motor that differs from the induction motor is that rotor should have low inertia, and that is achievable by having a smaller diameter. So the rotor should be having a smaller diameter in order to achieve lower inertia compared to two-phase induction motor. Now, just for the sake of quick recap of how things work in case of two-phase induction motor, because you studied about single-phase induction motor and you all have this thing in your home, you experience this daily, like your ceiling fan or other type of motors available in your houses. So most of them you'll find are single-phase induction. And if you remember, the single-phase induction motor works on the principle that the flux that is being produced by main winding and auxiliary winding are out of phase. And in order to create this flux out of phase, we use certain devices to achieve this. So auxiliary winding, if you place a capacitor in the auxiliary winding, so what you're going to do is you're going to have a phase difference in the flux because of main winding, because this capacitor is going to give you a phase difference between the IA, the current that flows through auxiliary winding, and the current that flows through main winding. So there will exist a phase difference between these two currents because of capacitor. So you try to make them out of phase in order to have flux corresponding to each current out of phase. And if you have flux because of auxiliary winding and main winding out of phase, then in that way you're going to generate a rotating magnetic field. So this is in case of a single phase supply. But let's say that I make the two windings in this manner, having the same supply, but the connections I only made them have extra wires and try to make them look like this, but they are still having the same supply. So this is the auxiliary winding, this is the main winding, this is the rotor, and here is the capacitor. So in fact, this is a capacitor run type induction motor. Now, if suppose that since I am talking about two-phase induction motor, I have the same windings, but instead of giving the same supply, the single supply, now I give two supply separately to both the windings. So instead of providing capacitor, what I am now doing is that I am going to give one supply VC, the other supply VR should be 90 degrees shifted from VC. So this is how again I am going to produce a rotating magnetic field around the rotor. And this will give the experience, this will allow the rotor to have current flowing within it because of inductive effects. So the current in the rotor will be produced because of the flux inducing it, and this will again experience torque when the current within the rotor will be coming under the influence of the rotating magnetic field. Now, in case of AC, in case of induction motor, if you look at this torque speed characteristic, this particular profile shows the characteristic of a two-phase induction motor. So in case of two-phase induction motor, you have a large reactance by resistance ratio. So in case of two-phase induction motor, and you'll observe that there exists a positive slope in this characteristic, then followed by a negative slope. So this positive slope is something which should always be avoided in case of control theories, because positive slope in control systems, positive slopes are always they always lead to instability of system. So this is what is written: positive slope in torque speed characteristics of induction motor poses instability if used in feedback control system. So if you're going to use a two-phase induction motor in a feedback manner, in a feedback fashion, then you cannot use that motor in this particular range, in the range where you have positive slope for torque speed characteristic. Then two-phase induction motor can only be controlled in the range where it has negative slope. So this is a shortcoming for induction motor, and this is not possible that you use this the induction motor in this particular range and you avoid this. So it will become very difficult for you to control within this limit and you avoid this limit. So instead of having that type of trouble and making things difficult or cumbersome, what we do is we provide higher resistance to the rotor. So if you're going to make resistance higher, the rotor resistance higher, in that case the characteristic is going to shift in this manner. So the ratio reactance by resistance becomes smaller because of higher resistance, and the profile gets like this. So in this particular profile, this is the profile for AC servo motor, while this is for two-phase induction motor. So if you look at this particular graph, then you see that there is no positive slope and the slope is now negative, which means that it can easily throughout the torque speed characteristic be used in negative feedback fashion. So this allows AC servo motors to be employed in control systems while two-phase induction motors are avoided in control systems. AC servo motors are designed to have linear torque speed characteristic, negative slope. So this is clear from this profile. So they have almost linear, not completely linear. So ideally, you assume it to be a straight line, but it's not. In practical cases, you don't have a very sharp straight line. So it's not going to be completely straight. You always have a slight curve in AC servo motors, but the slope should be negative. So this is the requirement. Negative slope is the requirement for things to be controlled. And in order, this is achieved by making the ratio x by r small by having high rotor resistance. So you're going to make this small by having r large, but there is a shortcoming, a drawback with AC servo motor, which is not associated with induction motor, is that you're going to lose power. So, but at the expense of power loss as heat in the rotor. So if you're going to increase the rotor resistance, this eventually will lead to power loss at rotor because of high resistance, and thus the efficiency of this motor drops. But you have a low inertia rotor that enables rapid acceleration from standard still. So having a rotor with smaller diameter and thus lower inertia allows you to control it very quickly. So it means that from standard still it can achieve high speeds within few within no time. So the desired characteristic from this we get is that it should have linear torque speed characteristic. Ideally, should look something like this. So the torque speed should be a straight line with negative slope. So shown over here are different profiles, different graphs, depending upon what control voltage you're going to give. So if you have a larger control voltage, the graph will be shifted outward. For smaller control voltages, control voltages means the voltage that is being fed at the control winding. So at this side. So if you're going to increase this voltage, so you're going to have curves like this going outward. The second requirement is that the slope of the torque speed characteristic must be negative. So this is what I explained in the previous slide. The characteristics must be parallel to another for various values of voltage, control voltage applied. So this is also shown in the graph. Now it is seen that when rotor resistance is increased, the torque speed characteristics become more and more linear. If you look at this particular curve, then if you're going to increase the value of r, this curve is going to shift downward, and as you keep on increasing R as much as possible, then you are almost going to get a linear line. In general, for low inductance to resistance ratio, the torque speed characteristic are almost linear. So I guess this explains about AC servo motors, and if you people have any question, you can ask me. So if anyone has any question related to field control DC servo motor or AC servo motors, you can ask. One thing I tell you about AC servo motor is that you can obtain the torque expression for it, but it's difficult because the torque speed characteristic for AC servo motor is not almost linear. So since we have a slight arc-shaped torque speed characteristic in case of AC servo motor, and thus instead of applying the conventional method to obtain the relation of torque, we from the curve apply Taylor series and obtain the approximate expression that fits to the curve of the torque speed characteristic. And from there we see that the torque is proportional to the control voltage as well as the speed. So the torque, because of AC servo motor, depends upon the control voltage given at the control winding and the speed of the load. So that is something because it's difficult to obtain while using Taylor series expansion of the. So first you will have to obtain the curve, the torque speed curve, exact curves. Then from that curves you will be applying Taylor series to obtain the final torque expression. So most of the books have skipped this part. I think core electrical books might have taken this and explained. So if some of you are interested in that, you can refer to books, and I can tell you how to obtain the torque expressions or give you the reference for the books. So any question?